have to do mi or I squared for each one. What some people did on that problem and had three masses distributed like that, they said they had already calculated where the center of mass of the system is, somewhere over here, and they had this clever idea: just take all of the mass at the center of mass and calculate the moment of inertia as I equals the total mass r squared, where r is the distance to the center of mass. Very sweet. In other words, to calculate moment of inertia, concentrate all the mass at the center of mass. Very sweet, but it does not work. It doesn't work for calculating moment of inertia. In fact, I can give you a very simple example. Suppose that I had a sphere, and I applied the same reasoning to the sphere, and I said I want to calculate the moment of inertia about an axis through the pole. So the people who do it this way say, well, you can concentrate all the mass at the center of mass. Well, let's write out the center. And then calculate the moment of inertia as total mass times r squared. Well, r is 0. In that case, we conclude that the moment of inertia is 0, which it is not. It's 2 fifths mr squared. So there's an indication that there's something wrong with this method. In fact, we know from the parallel access theorem exactly what's wrong with the method. The moment of inertia about this point over here would be equal to the moment of inertia about the center of mass plus the mass, the total mass, times the distance squared, what we called h before, but in this case would be just m times r squared. So when you concentrate all the mass at the center of mass and take mr squared, you got that term, but you didn't get this term. The moment of inertia, you could write the moment of inertia here as the moment of inertia about the center of mass plus mr squared. That would be perfectly legal. In fact, I believe a few people did it that way, although it's kind of cumbersome. But what you can't do is just take the mr squared, as though you concentrated all of the mass at the center. That works for some purposes, but it doesn't work for calculating center of mass, the moment of inertia. Just wanted to mention that because actually I thought that it was a nifty idea, and it sounds like the sort of thing that would probably work, but it doesn't. It should work. Last time I started the subject of special relativity, let me put back in more refined, more refined form the two postulates on which Einstein based the theory. Remember, this dates from 1905. Two postulates. First, the principle of relativity itself. Principle of relativity is the first postulate of the theory of relativity. The principle of relativity says that the laws of physics apply in any inertial reference frame. What does inertial mean? Well, naively, it means at rest or moving with constant velocity. As I was mentioning at the end last time, that actually is a defective definition, because how would you know if a system is at rest? If the laws of physics apply perfectly well in any moving reference frame, you have no way of knowing what is a system of rest, ascertaining what is the rest system, if indeed there's any such thing as a rest system. And if you don't know what a rest system is, how do you know what one moving at constant velocity is? That would be constant velocity with respect to that rest system. So naively, that's what everybody is thinking about when they say an inertial reference frame is one that's at rest or moving with constant velocity. But actually, that's a defective definition. It's circular when you press it. The more sophisticated definition of an inertial reference frame is it's one in which Newton's first law, the law of inertia, holds. That is, it's a reference frame in which objects are going with a constant velocity keep on going with a constant velocity unless acted upon by some force. So if you're out in outer space and you want to know, am I in an inertial reference frame? You throw a bunch of ping pong balls around, and if they go in straight lines with constant speed, then you conclude, well, probably I'm in an inertial reference frame. And then any frame moving with constant velocity with respect to that is also going to be an inertial reference frame, but I never had to tell you anything about a frame at rest. So that's the more sophisticated definition. By the way, it puts a funny twist on Newton's first law, because it means that Newton's first law is, in a sense, is true by definition. What Newton's first law tells you is what is a legal reference frame for doing physics. It defines the legitimate reference frame for doing physics, anyone in which that law happens to hold. The second postulate of the theory of relativity is the universal speed of light. Which says that the speed of light in vacuum is the same in all inertial reference frames. By the way, for the purposes of this discussion of relativity, when I say the speed of light, I always mean the speed of light in vacuum, okay? Sometimes I forget to put that in parenthetically, but we're always talking about the speed of light in vacuum is the same, namely c equals 3 times 10 to the 8 meters per second in all inertial frames. Regardless, in other words, of the motion of the source, or of the detector, or of any presumed light-propagating medium. That's the universal speed of light. As I mentioned last time, the principle of relativity itself was ancient news, well known to Galileo centuries before Einstein. If Einstein added anything to the story of the first postulate, it was just a statement that it applies to all of the laws of physics known and yet to be discovered, whereas Galileo would probably have been more modest and said it seems to apply to the laws of mechanics. But the first postulate was not revolutionary. The second postulate was the revolutionary postulate. In fact, as I tried to argue last time, absurd on the face of it. Although Einstein wiggled out of the apparent contradiction by introducing a new formula for the combination of velocities, the addition of velocities. I should pause right now and tell you why on earth Einstein would have done something so weird as to propose the second postulate. Because I'm a little concerned about the time today, and I want to make sure that I've got the information that you need for the owls for Wednesday, I'm going to reverse the order and put on hold the explanation for why Einstein adopted the second postulate, and we'll come back to that at the end. So. Logically, right now, I should address that issue. But for reasons of convenience, I'm gonna hold off on it for a moment. But I will come back to that either today or on Wednesday. What I want to do now is start assembling some of the implications of special relativity. There's a danger in this business, by the way, that you will get the sense after we've gone through 2 or 3 of these implications that just everything you ever believed is out the window, and therefore, where's the firm ground to stand on? I'll tell you in advance that there are actually 4 basic effects of relativity, and once we've done those, it's not as though every time you turn around, there's going to be some new bizarre effect. There are 4, and once you adjust to those, that's pretty much it. So, number 1. The relativity of simultaneity. What I'm going to do is introduce each of these with homely little parables that are due originally to Einstein. As I think I mentioned last time, Einstein loved to tell a story in terms of these little Gedanken experiments that sound awfully innocent and cheerful. Let me warn you that they are very brilliantly designed to avoid 1,000 minefields. So they're, in some respects, they're a little bit too nifty, because they are often, they're absolutely honest, but they come awfully damn close to someplace you could trip up. So, relativity of simultaneity. Here's the first parable. Suppose that I've got a boxcar and a train, and I have manufactured a light bulb that I carefully hang from the very center of the boxcar. Center down here, I mean center as far as forward and backward is concerned. And at a switch I can turn on the light. Now I have mounted also a couple of detectors, a detector on the front wall and a detector on the back wall, and those record the event when the light signal gets to them. Maybe they ring a buzzer or something like that. Let's call this one A and this one B. Those are 2 detectors then. Now, here's the idea. At a signal, I switch on the light. The light expands out in both directions, hits these 2 detectors. Question, which detector does it hit first? Let me define the 2 events here to be very precise about it. Event A is that the light signal reaches the front detector. The train itself is going to be going to the right. That's why I said that's the front detector. But we're looking at it from the moment, just from the point of view of the boxcar itself. Maybe you're an observer sitting inside the boxcar. Event A, light reaches front detector. And event B is light reaches back. Question, which happens first? Well, it's a stupid question. I built this thing with the light bulb in the very center. Light travels out at the same speed in both directions, got the same distance to go to both of them. So they must happen at both at the same time, which is to say simultaneously. It's easy. Of course, in classical physics, you might be worried, well, gee, am I dead sure that the light travels the same speed in the forward direction and in the backward direction? In relativity, you don't need to worry about any of that stuff. The second postulate says speed of light travels the same in both directions, regardless of the motion of the source, if the boxcar is moving or anything. It just travels at the speed c times 3 times 10 to the 8 meters per second, both ways. An easy question. That's the simple part of this one. By the way, pay close attention to this because I once taught a course in special relativity in which the very best student in the class asked me a question on this after the last lecture, and I suddenly realized that this guy had not understood anything that I've been talking about in the whole semester because he had not understood this one point. It is always, of course, possible to be mistaken about which one happened first. In fact, if you happen to be sitting right under detector B, for example, and detector B sends out a buzzer or something like that, so that when the light hits B, the buzzer goes off, and when the light hits A, the buzzer goes off, and you and I know that those two buzzers went off simultaneously. That's the argument I just gave. But if you happen to be sitting in this corner, you might actually hear the sound from B, before you heard the sound from A, for the stupid, obvious reason that it took less time for the buzzer, the sound, to get to you. It's got nothing to do with when the actual events occurred. It has to do only with how long it took the news to reach you. Any fool, long before Einstein, would have made the obvious correction for how long it takes the news to reach you, whether it comes by sound, or by radio waves, or by carrier pigeon, I don't care. Whatever method it was that got you the message, of course you're going to correct for the time it took that message to reach you, right? So, in relativity, we're not dealing with this stupid issue, how long did it take the message to get to you. We're dealing with a serious issue, what was actually happening here. There's several ways that, if you read in the books, they go a long song and dance about this issue, several ways that you could handle this situation. Either you do sit in that corner, and then of course you hear buzzer B first before buzzer A, but then you figure out how long it took the sound to get to you from each of them, and after you've done the calculation you say, wow, those two things were simultaneous. They really were simultaneous. Or another thing that you could do is you could sit yourself in the very middle of the car so that you're getting the two messages simultaneously because they got the same distance to travel with you. Or you could get a friend and have your friend sit in this corner and you sit in this corner or right up next to the buzzer, each of you with a stopwatch and a clipboard or something like that. And the moment the buzzer goes off there, you record the time. The moment the buzzer goes off there, you record the time. Then at lunch you get together and you compare notes and you say, wow, those two things happened at the same time. I don't care how you do this, but this is a stupid, obvious problem. Relativity is not dealing with that. Relativity is dealing with what you got after you made the obvious correction for the time the news took to reach you. Okay? In relativity, it's useful to distinguish what you observe from what you see or what you hear. What you observe is after you made the obvious correction. For the time it took the news to reach you. From what you see, hear, etc. That would be the sort of raw data before you made that obvious correction. Relativity's got no interest in what you see. It's interested in what you observe. A photograph, for example, is not an observation. But a photograph, the more distant stuff, is actually happening earlier, right? Because the light took a while to get to you. Or if you look out at the night sky, you're not making an observation of the night sky. What you're seeing are nearby stars right now, distant galaxies hundreds of years ago. So that's not an observation. In fact, we'd have to wait 100 years until all the news has come in before we could observe the night sky tonight. An observation is not something you do in the moment. It's something you do later after you've collected all the data. Relativity deals in observations. So the word observation or observer is actually a technical term in this business. It means the guy who's had the sense to make the correction for the time the message took to get to you. Enough on that sermon. As I said, I wouldn't shout it so loud, except that I was really burned on that once in the past. So, event A and event B are simultaneous, according to somebody who's riding along on a train. But how does this same thing look from the point of view of an observer standing on the ground? Well, here's the boxcar. And the light bulb, the very center. And somebody switches on the light bulb. But now, from the point of view of the person on the ground, of course, the boxcar is moving along to the right with some speed v. So, as the light signal goes out from the light bulb in both directions, the train itself is moving. By the time it reaches the back end, the train has actually moved, the boxcar has actually moved over into this position here, and now detector B fires off. How about detector A? No, the light signal does not yet reach detector A. It's only gone an equal distance in the forward direction, but detector A has meanwhile moved further over to the right. So I haven't got to A yet. In fact, it'll be a moment later when the thing has moved into this position when the light signal finally reaches detector A. You see the point? Because the boxcar is in the meantime moving, the light has to go a shorter distance to the rear end than it does to get to the forward end. And therefore, detector B fires before A. The reason for that is light has a shorter distance to go to B because of the motion of the car. Make sense? Why didn't that happen in classical physics? Oh, well, in classical physics, there was no second postulate here. The speed of light was not the same for all observers. We would have said in this case that if the speed of light is c in both directions for an observer riding along with a boxcar, then in this case it's faster than c in the forward direction and slower than c in the backward direction, picking up the velocity of the boxcar itself. So it goes a longer distance in exactly the same amount of time, and the two would have been simultaneous anyhow. But given the second postulate, those two events which were simultaneous in this reference frame cannot be simultaneous in this reference frame. By the way, you might say, well, gee, one of them's right and the other one's wrong. No, the first postulate says that all inertial reference frames are equally valid for applying the laws of physics. If you believe the first postulate, you cannot say, well, this guy is right and this guy is wrong. They're both equally right. Both of them are legal observers in the sense of the first postulate. So it all fits together. It simply is the case that two events which were simultaneous according to one inertial observer are not simultaneous according to some other inertial observer. We call that the relativity of simultaneity. Einstein used to say that all of the basic mysteries and paradoxes of relativity ultimately reduce down to the relativity of simultaneity. That's such a new and surprising notion that it's very tough for us to adjust to it intuitively. I think he was right too, that all of the paradoxes of relativity ultimately reduce down to the fundamental paradox, the relativity of simultaneity. So, conclusion. Two events that are simultaneous would happen at the same time. That's the relativity of simultaneity. And remember, it doesn't have anything to do with the fact that you might have been nearer to one. So, you know, kids think that that lightning comes first and thunder comes after. You and I know that actually the events, the thunder and the lightning, were simultaneous. But one of them came to you at the speed of light, one of them came to you at the speed of sound. So it's natural for kids to think that one happened first and then the other. But we know that if you had made the obvious correction, if you had observed, then you would have said that they were simultaneous. Same sense here. I'm not talking about some kind of a mistake because of your location or something. It's simply the case. Item 2, time diagram. Another of Einstein's little parables. This time I'm going to use the same equipment, but I stick a detector on the floor directly below the light bulb. At a distance h. So here's the picture, boxcar, and I'm going to do exactly the same job. I'll analyze it first from the point of view of somebody riding along with the boxcar, if you like, in which the boxcar then is at rest. Here's the light bulb, here's the detector, and the distance that the light has got to go is h. So there's the light beam, and it goes a distance h down to the detector, and the question I ask is, how long does it take the light to get from the bulb to the detector? Question? Well, in this reference frame, it's easy. How far does it have to go? H. How fast is it going? C. Always going to C. So the time, which I'll write with a prime on it for reasons you'll see in a moment. I'm going to use primes for measurements that are conducted on the train car as opposed to measurements conducted on the ground. So C delta T prime is equal to H, the velocity times the time equals the distance. Or delta T prime, what I was trying to calculate, the time it takes the light to get from the bulb to the detector, as measured by an observer on the train, is H over C. So far, so good. That's the easy one. Now let's analyze the same process. Same process, but from the point of view of an observer on the ground. This time I'll call it delta T, the time as measured by an observer on the ground. Why is the situation different? Well, of course, same reason as before, because the train has meanwhile been moving. Here's the situation when the light leaves the bulb, but while the light is propagating down to the detector, the train itself is moving along to the right. So here's the configuration it's in when the light beam finally hits the detector, which is now over here. So that light signal, same damn light signal, by the way, same signal as that one, and from the perspective of somebody on the ground, went that diagonal route. Had to go somewhat further. In fact, how much further? Well, the height here was h. How far did the train move? Well, let's say delta t is the time it took, delta t with no prime on it, is the time it took for this process in the reference frame of the ground observer. Then the distance the train has moved is v, the velocity of the train, times delta t. Isn't that right? If this train is going along to the right, and I wait for a time delta t, the time it takes that light signal to get down there. V delta t is how far the train has gone. How about the diagonal length there, the distance that the light signal traveled? Well, that light signal was going at the speed c. As I said before, these analyses are in some respects a lot easier than they would have been in classical physics, because I never have to confuse my mind about how fast the light is traveling. The light's always going at speed c. So c, the light has to go this diagonal distance. C delta t is the distance that the light traveled. Velocity of light times the amount of time it took. Well, looking at that triangle there, I see c squared delta t squared, the hypotenuse squared, is equal to the sum of the squares of the other two sides, h squared plus v squared delta t squared. Make sense? From this, I'm going to calculate what delta t is. That's the time it takes for this process as measured by an observer on the ground. I already know the time it takes as measured by an observer on the train. Now it's just a little bit of algebra to figure out what that delta t has got to be. Let's see, I'll bring the delta t's together, so I've got c squared minus v squared coming from the other side there times delta t squared is equal to h squared. Divide through both sides by c squared, then this would be 1 minus v squared over c squared delta t squared equals h squared over c squared. But h squared over c squared is precisely the time interval as measured on the train. So this is delta t prime squared. What does this tell me? 1 minus v squared over c squared times delta t squared equals delta t prime squared. I'm going to divide this stuff over to the other side and take the square root, and it would say delta t is equal to 1 over the square root of 1 minus v squared over c squared times delta t prime. That's the conclusion. Or let me introduce some nice notation, write this nicer. That factor, 1 over the square root of 1 minus v squared over c squared, is a ubiquitous factor in relativity. It comes up time and again. So it's handy to have a notation for that. We call it gamma. Gamma is by definition 1 over the square root of 1 minus v squared over c squared. Notice, by the way, well, let me ask you, is gamma a number larger or smaller than 1? It's larger, isn't that right? Because in the denominator, say I was going half the speed of light or something, this would be 1/4 then. I've subtracted something from 1, so the number in the denominator is less than 1, and therefore the number gamma itself is greater than 1. Yeah? I don't know what to say about putting in velocity equals c. But you know what? I think I don't have to confront that question, because you can't get a boxcar going at speed c. If you could, I agree with you. We would be in some kind of a quandary here about exactly how to interpret this formula. The time interval would actually be, well, depending on how you look at it, it would either be infinity over here or it would be 0 over here. A weird thing. But no observer, no inertial reference frame can ever go at the speed of light. You'll see why that's true. We take an infinite amount of energy next week. So this is our first indication that probably things better go with a speed between 0 and c, but no faster. Otherwise, things start to go haywire. They do go haywire, but this is not the only one.
If velocity is c, I think it will never touch the detector.
Well, I won't quarrel with you about that, but I think it's more safe to say there's no such thing as an inertial reference frame going at the speed c, because the moment you allow yourself to be an observer traveling at the speed c, this is not the only thing that goes crazy. Fortunately, no observer can go at the speed c. That's also built into the theory. So the issue doesn't arise, although you wouldn't know about it at this point. At this point, you just say something fishy when v is equal to c and hope that it never happens. I guess that would be the safe way to put it, yeah.
What is delta t prime?
What is what?
Delta t prime.
Delta t prime, remember, was the time it took the signal to get from the bulb to the detector according to an observer who's on the train. Delta t is the time it took for exactly the same process according to an observer on the ground. By the way, I've had people also in the past say, oh, well, in this picture, the light was going along a diagonal line. It's obviously a different piece of the light, or whatever that means, than the light here. No, it's exactly, if you like talking the photon language, a single photon went from the bulb straight down to the detector in that reference frame. That same photon, viewed from the person on the ground, went along a diagonal line. How do I know that? Well, it left from the bulb and it arrived at the detector. So, I'm sorry, it had to go along the diagonal line. That's all there is to it. So where are we? Greek gamma was this factor, and is everybody persuaded that this is a number greater than 1? Under what circumstances would it be 1 itself, by the way? If v was 0. If v was not moving at all, if the thing was not moving at all, then v is 0 and gamma becomes 1. But if the boxcar is moving at all, then that gamma number is a number larger than 1. It's handy to have that always in the back of your mind. Gamma, when you see it, gamma is always bigger than 1. Or rather, bigger than or equal to 1, and equal to 1 only in the kind of trivial case where the thing isn't moving at all. Gamma is greater than or equal to 1. So now let me write my final formula here. It says delta t is equal to gamma times delta t prime. That's the time interval as measured by somebody on the ground. This is the time interval as measured by somebody on the train. By the way, the fact that what we were measuring happened to be a light signal going from the light bulb to the detector now turns out to be irrelevant. This is simply the ratio of the time interval for any two events is going to be in the ratio gamma as measured on the train or as measured in the on the ground. Let's think what this means. Suppose, for example, knowing that gamma is larger than 1, let's take an easy number. Suppose that gamma was 2. I don't know what v would produce 2, but there's some velocity that would produce a gamma of 2. And let's say delta t is equal to 10 minutes. Then what would delta t prime have been? I lost you?
5.
It would be 5, isn't it? No, you've got to multiply the delta t prime by 2 to get 10, so this would evidently be 5 minutes. So for a process that took 10 minutes by a ground observer, it would take 5 minutes by the train observer. What exactly does this tell you? Suppose that we looked at the two clocks. A clock moving along with the train. The clock moving along with the train ticks off 5 minutes, when our ground clock ticks off 10 minutes. What will we make of that? We'd say, hey buddy, your clock's running slow. Isn't that right? Because our clock ticked off 10 minutes, it's only ticked off 5 minutes, so the moving clock, the clock on the train, is evidently running slow. How slow? By a factor of gamma. Conclusion? Moving clocks run slow. How slow? by a factor of gamma. Personally, I can never remember which side is supposed to have the primes on them, and as a matter of fact, from one book to another, you will see different conventions. Some people will put a subscript on here or something. But listen, time dilation is beautifully simple to remember. Moving clocks run slow. How much? Factor of gamma. You stick the gamma on whichever side of the equation you need to make it come out that the time interval on the moving clock was less than the time interval on the stationary clocks. It's easy if you don't become a slave to the equations and instead think about what's happening. Moving clock runs slow. How much? Factor of gamma. Of all of this is what we call time dilation. Of all the effects of relativity, this is the easiest to check in the laboratory. Actually, time dilation is bread and butter physics in any elementary particle laboratory, such as Fermi-Lab or SLAB or something like that. Why is that? Because elementary particles, most elementary particles, spontaneously disintegrate after a certain amount of time, what we call the lifetime of the particle. That means that every unstable elementary particle is itself a tiny little clock. It's a clock that only ticks once, but never mind, that'll do. That'll do as far as we're concerned. It's born and it dies. It's got its lifetime there, and that lifetime constitutes a tiny little clock. A clock that we could get going very close to the speed of light. You might have said, how are you ever going to detect it? By the way, gamma is very close to 1 as long as you're at small velocities. I should mention that. Why didn't we ever notice this before? Because the gamma factor for ordinary velocities is very close to 1, and you're never going to detect the difference by taking an actual physical clock and moving around or using your watch. The velocity is just nowhere near enough for this correction factor to be significant. But it so happens that we have tiny little clocks that we can get going at the speed of light, or close to the speed of light, namely these unstable elementary particles. So, easy to check in the lab. Most elementary particles are unstable. Disintegrate spontaneously, that is without nobody has to pound them with a hammer or something, they just disintegrate spontaneously. After a lifetime, that's characteristic of the particular particle species. For example, a muon, the muon's lifetime is 2 times 10 to the minus 6 seconds, millionth of a second, 2 millionths of a second. The neutron is about 10 minutes. And if you look in the tables, you can find all kinds of elementary particles, each one listed with its own characteristic lifetime. Now the lifetime they're going to list in the books is the lifetime of that particle if it's at rest. Or another way of saying it is in its own reference frame, where of course it is at rest. Sometimes called the proper lifetime. When the particle is at rest. But suppose one of these particles is moving at high speed through the laboratory. Then its internal clock, whatever it is that tells it when its time is up, its internal clock runs slow. As a consequence, that particle can last very much longer than it would have at rest. So even though you look up in the table that the lifetime of a muon is 2 times 10 to the minus 6 seconds, if it's going at high speed through the laboratory, it might last quite a lot longer than that. In fact, this happens every day in elementary particle labs. Let me do an example. I'll use the muon since it happens to be the one I listed the lifetime for, that's the lifetime of a muon at rest, is 2 times 10 to the minus 6 seconds. How much longer? A factor of gamma. Because their internal clock is running slow. It's like your internal clock that tells you when your 85 years or whatever is up. But if it was running slow, you might last a whole lot longer. Not from your own point of view, by the way, but from the point of view of other people watching you fly by, they would say, wow, that guy lasted 100 years. Because your internal clock, your heart rate, your metabolism, everything was running slower. Well, you didn't live longer, by the way. You lived slower. You didn't think any more thoughts than the guy on the ground did. You just thought him slower. Where was I? Example? Yeah. Example. Suppose that a muon is going through the lab at, let's say, v equals 3/5 the speed of light. How long does it last? Well, I can figure out what gamma is for such a muon. 3/5 is 1 over the square root of 1 minus v, which is 3/5 c divided by c quantity squared. By the way, you should always love it if somebody gives you velocity as a fraction of the speed of light, because then the c's in a formula like this cancel out, and I just get 1 over the square root of 1 minus 3/5 squared, which would be 9 over 25. If I multiply top and bottom by 5, I get 5 over the square root of, inside the square root sign is 25, and it kills the 25 there. 25 minus 9. 5 over the square root of 16, which is 5 over 4. You will soon discover that in special relativity, everything seems to be going at 3/5 the speed of light. Or maybe 4/5 the speed of light works for that, or 12/13 the speed of light works too. Those happen to be fractions such that gamma turns out to be a nice pure fraction, and there aren't a bunch of square roots all over the place. So, anyhow, 3/5 the speed of light. Why did I choose that? Because I knew gamma would come out nice that way. Gamma is 5/4. So how long does this thing last in the laboratory? 5/4 gamma times. By the way, bigger than 1, right? It's supposed to be. If you're ever doing a calculation like this, and you get a gamma that's less than 1, scan it for that, because that means you made a mistake. Most likely, you forgot that gamma is 1 over the square root. It's not just the square root. Very common error to make. So 5/4, number bigger than 1, times the time it would have lasted in its own reference frame, the 2 times 10 to the minus 6 is, let's say, 2 goes into 4, 2, 5 halves is 2.5. So 2.5 times 10 to the minus 6 seconds. Not a huge increase in that case, because this thing wasn't going all that damn fast, but it's a substantial increase. Instead of lasting 2 times 10 to the minus 6 seconds, this thing going at 3/5 the speed of light would, from our perspective in the laboratory, last 2.5 times 10 to the minus 6 seconds. Of course, a muon doesn't think it lasted any longer. In the muon's own reference frame, it lasted exactly 2 times 10 to the minus 6 seconds. It's us looking at it from the outside who say that muon lasted longer. But if you were doing a measurement in which, for instance, the muon was a track in some kind of an emulsion or something like that, the track would be 5/4 longer in the laboratory than you would have calculated had you not known anything about time dilation. So time dilation, as I said, very easy to measure in the laboratory. I have not done what I promised to do to tell you why Einstein proposed the first postulate, but hold on, I will do that.